Hi everybody. Today we're going to go over a quick trick of how to unpack Qbot malware. Qbot or Quackbot is a common banking malware that you'll almost always find packed. So you need to be able to unpack it in order to do a full in-depth analysis, oftentimes to find the IOCs, maybe to run YAR rules against it, or even antivirus signatures in order to even identify it as Qbot. And so you really want to be able to know how to manually unpack it. We're not going to go super in depth in the process. We're going to go over just a quick trick to kind of help you out. You can always use automated solutions like Unpack Me, but it's always good to know how to do it manually too. You may not want to use an automated solution because maybe your file is sensitive and you don't want to upload it to a public service. Maybe the automated services don't work. You need to build it manually, or it has like anti-debugging tricks in it. So most of those cases aren't the case for this Qbot. But it's good to basically practice it so that when you do get a case that you can't use an automated solution, you know how to do it manually. So this video is going to start off with just a little bit of the overview of how the unpacking process works, and then we'll go into the trick of how to unpack it. And then finally we'll end with a little bit of a deeper in-depth look at the Unpacking Sub. Not too in-depth, but just a little bit more so you can see the unpacking steps and what they look like in assembly. So let's go over start with the general unpacking process. So when you unpack malware, you're always going to do the same basic steps regardless of the unpacker. You're going to decode the payload. That's going to be either decrypting it, decompressing it, or both. You're going to allocate heap memory for the map file. And then you're going to map the file state into the memory state. And that consists of copying the headers to the heap, copying all the sections over, fixing the relocations, building an import address table, and then finally applying section permissions. After all that's done, you're just going to call the address to entry point. So I want to take a minute to note this map file state and kind of show what that looks like. So if we open up this sample in PEBear, and we go to the section headers, we can see that we have this raw address and this virtual address. The raw address is the file state, and the virtual address is where you're going to map it into the memory state. The way to think about this is the file state is really a compressed form of the memory state. That's because in memory you're going to have things like variables initialized as 0, uninitialized variables, and things of those nature. You don't want to have a bunch of null or 0 variables in the file state, because then your file size just gets bigger for no reason. And so your file state's always going to be, or almost always going to be smaller than your memory state. And so when we talked about that mapping process, we're taking each section one by one. For instance, the text section starts at 400 hex in the file state, and we're going to copy that into the memory address, the heap memory, at 1000 hex. Same thing for the R data. We'll go from 14600 up to 16,000. And we're going to do that for each of the sections. And that's how we're going to basically expand it out into the memory state. So the reason that's important is if we go on to the unpacking goals, is our goal for unpacking is a copy from memory when the payload is decoded, but before it's mapped in memory state. And the reason you do that is because you want to preserve your hash. So if you go back to these steps, you can see that if you map this file state, you're going to be modifying your binary in memory based on your environmental indicators. So you're going to have these fixed relocations, you're going to build the import address table, and then you're going to copy the sections to the heap. As we mentioned, these copied sections heaps will change the location. So instead of going from 400 hex for the text section, you'll go to 1000 hex. Your relocations will modify it based on where it got loaded in memory from ASLR. That means every time we dump it out of memory, if we dump it after this map file state is done, we're going to have a different hash because potentially we have a different image base. That means our relocations could be different every time. And so if we unpack this 5 different times and we get 5 different ASLR addresses for the image bases, we'll get 5 different hashes when we dump this out of memory. So what our goal then is to dump it out prior to this map file state, somewhere after the step 1 or 2. So basically before we get to implement step 3. And that means we won't have any of this, fixed relocations. We won't have these sections expanded out. We won't have the section permission changes. None of that stuff is going to be performed. So we're going to have the file in their kind of pristine file state. And so then again, if we had the same example where we have 5 different packed samples, all with the same payload, if we dump them out at this step 2, then that means the hashes are all going to be identical because we didn't modify any of the file with the kind of environmental artifacts. If we dump it out at this step 4 and just do a straight memory dump, we'll get a different hash probably every time we dump it out. And so that's why our goal is to dump it out from the after it's decoded, but before it's mapped in memory state. The way we're going to dump these out, the trick we're going to use, is really understanding how the unpacking process works. So that involves knowing two different aspects. First, the payload is rarely decoded in place. It's usually decoded into new memory. And that means we're going to be watching newly allocated memory for a decoded MZ header. The second aspect we want to think about is that the decoded payload is generally mapped to a new memory, and that could be in a new process or a new heap memory. That requires a read access from the memory holding the decoded payload in file state. So our trick is going to be put read and write breakpoints on new memory, and basically just watch for the read-write sequence to find the decoded payload in the file state and copy it out of the memory from there. And then we'll just do a little bit of cleanup to make sure there's not any like trailing zeros or extra padding. And then we'll have the kind of pristine file state and can compare our hashes to other unpacked samples. All right, so with that, let's go ahead and go into a couple examples. And we have, let me go ahead and close this PE bear. We have two examples here. Both the hashes are in the video description, and you can download from malshare.com to practice on your own. So let's pull up the sample one in X32 debugger. I'll hit F9 to get into the user space, and then I'm just going to hit Control-G and go to virtual Alec. And I'm just going to hit F2 to put a breakpoint. And all I'm going to do is F9 until I hit this breakpoint. Virtual Alec is the most common memory allocation API, and so for a trick, that's generally all we look for. So we'll give this a second, and we hit a virtual Alec, and then we're going to hit Control F9 and F8 to get back to user space. And then hex dump, we do Control-G and EAX. And then I'm going to put a breakpoint on this first byte. So I'm going to select it and do right click, breakpoint, hardware, I'm going to do access and a byte. I'm not going to do a write. I wish I could just specify read or write, but you read or write separately. But the access will do read and write, and we have no breakpoint just for the read. So we're going to do the access to do read and write. So I'm going to F9, and you can see we got our first byte written out. So I'm just going to F9 basically a couple more times. So that was one more time. We'll do 2, 3, 4, 5, 6, and then 7 times. And we see all we're looking for is that when we get some type of decoded information. We can see here we have what looks like in kind of API list. And if we scroll past the API list, we have what looks to be the kind of compressed DOS header. We can see what looks like here, this program cannot be run in DOS mode in some type of encoded state. It looks compressed here as opposed to encrypted. So what I would expect is if it's compressed, is that you rarely decompress something in place because you're going from a smaller state to a bigger state. So normally you decompress it into new memory. So I'm going to expect another heap like virtual Alec to be called. So I'm going to just F9. And I'm just going to F9 a couple times until I see basically hopefully another virtual Alec or this file get decoded in place. So I'm really just looking for the MZ header. And now that last F9, you can see here I got the kind of spinning wheel. And so I didn't see a decoded MZ header, but I really went too far, and then it's already unpacked and kind of running the background. So I'm going to reset this, and I kind of went over that to show you an example. So that one didn't work, and so we need to actually modify our trick just slightly. So I'm going to hit Control-G and go to virtual Alec. I'm going to take this breakpoint off. And what's to note here is you notice this virtual Alec is in kernel 32 if you look up at the title bar here. And this calls into the virtual Alec. So I select that, hit enter. And then if we look at the title bar, it's in the kernel base. I'll put a breakpoint in there and then F9 until I hit it. That means kernel 32 virtual Alec calls kernel base virtual Alec. Most of the time when APIs or when malware calls a virtual Alec, it calls a kernel 32 API. And in this time, it does do that the first instance. But the second instance, when it needs to allocate memory for the basically decompress the payload, it actually calls kernel base directly. So one of the kind of tricks you use instead of putting the breakpoint on kernel 32, you want to go ahead and put it on kernel base virtual Alec. That'll work most of the time. You could go down into anti-DLL functions that the kernel base virtual Alec calls, but that gets a little bit more complicated and it's only needing a small percentage of time. So just as a general trick to make it easier, I'll tend to use kernel base virtual Alec. And if that doesn't work, then I'll look at a lower level API. So now that we hit our breakpoint, I'm going to hit Control F9 and F8, and then I'll do a I'll hit Control G, and I'll go to EX to follow my memory and put my breakpoint. So right click, breakpoint, and then hardware access with a byte. So just like before, I'm going to hit F9. I see my first byte writing out. Then I'll F9, couple more times to get to the first decoded state. And we see here we have our API list, and then what looks like the compressed MZ header. The funny thing, this is actually not compressed, it's encoded, and we'll show you that after the video, but it really does look like compressed, in here. So this one's a little bit tricky. So we hit F9 again, and then a couple more times, and then let me do a few more times until we get to the... So we can see here these are still changing, so I'm still just doing F9 until I either see this decoded, or here we got to my virtual Alec. So that probably took me maybe around 10 times or so. And again, always looking to see either did my memory get decoded state where I saw the MZ header, or I get to another call to virtual Alec. So since I got a call to virtual Alec, I'll control F9 and then F8. And then in this dump 2, I'm going to do control G, go to EAX, and then put my breakpoint right here. So right click, breakpoint, and hardware access. And then I'll F9. I see my first byte writing out. F9 again. So I got here now what looks like the top of my file, but we don't have the API list there. So I'm going to, so my expectation now is that the next step is going to decode this, and then I'm basically going to go through and decode it, and then at some point I'm going to read this decoded file in order to map it into memory. In Qbot, we actually overwrite it in the original entry point, so we won't get another call to virtual Alec, but either I would get another call to virtual Alec, or I would see that it's going to be copying this file state into a new process, for like process hello and type injection into new heap memory or into an existing data section. So we're going to do F9, 1, 2, 3, 4 times, and we got the MZ header down here. One more time, and we got the full decoded MZ header. So now that it's decoded, we can look here at the part we broke to. So basically just going, so this break is on the read access for this MZ header. And so now if I look at the structure that I broke on, I'm grabbing a byte from EDX and moving it into ECX through the AL register. If I look at EDX, I see this is 2300000. That's the address that this decoded MZ header is. And then it's writing it into ECX, which is 400,000 hex, or basically the original entry point, or the of the code. So that means we're going to be overwriting this into that original section. I know this is in the file state because if I scroll down here, I'll scroll until I see some null padding, so that's the end of the header, and then my first section starts at 400 hex. If we open this back up in PEBear and go to the section headers, we see that our text section starts at 400 hex. So probably a good 90% of your files, especially for the 32-bit files, the text section is start at 400 hex. Sometimes it'll start at 600 and occasionally start at like the 1000 hex, but most of the time you're going from 400 hex to 1000. So just as a quick verification, you can look in your debugger, and if you have your text section starting at 400 hex, basically the end of a null padding, and then new code started at 400, you know you're in the file state. If you have more null padding there, and you go to 1000 hex, and you see text starting there, then that means you're probably in the memory state, or you're in one of the niche cases where the text section starts at 1000 hex. In that case, you'd have to look a little bit closer into the section headers and start doing more investigation. But this one's pretty simple to determine. So all we're going to go is go to the memory map. We're going to go to the 230, and we're going to right click and dump memory to file. I'm going to put this in my demo folder and hit save. And all we need to do now is basically clean it up, because we dumped out the entire section out of memory, but usually the files don't go all the way to the end of the section. Normally they stop somewhere short. So we need to clean off any trail and zeros that we dumped out of memory so that we get the exact hash that we're expecting. So I'm going to open this up in PEBear, and we're going to go to the section headers. And all we're looking, we know it's the raw state, so it's the file state. We're going to the last section, and we're taking the start of the last section and add the size. So let me open up a calculator. And so I'm going to do this at 35400 plus Charlie 00, and that takes my relocation section, add the size, and so I can see my file is going to 36,000 hex. So let's go ahead and open this up in HXD, Control G, and 36,000. And we actually see that's the very end of the file. So in this case, we don't even need any cleanup, and that file is the dump file in the file state, and there's no fix-up that needs to be applied. So if we go back to PE bearer, we could see our hash here, the SHA-256, as the F5, FF6 delta, and that is our hash we'll get every time when we dump this out, as long as we had the identical payload, because we didn't modify it with any of our environmental indicators like the relocation, image base, the fix-up, IAT, and things of those nature. So that's all there is to it. So let's go ahead and do one more sample. The second sample is actually going to be a little bit easier, but just to show you how that they can vary a little bit, and how the trick that generally just always works. Sorry, I hit the wrong program. Let's open this sample 2 in X32 debugger. F9 to get in the memory space, and then Control G, virtual Alec. Sorry, you have to do, I think, case sensitive. So virtual Alec. And then I select the second one, hit enter, and put my F2. I'm going to do F9. And this one's actually a little bit easier because it only calls this virtual Alec once, and then it decrypts it in place. So we give it a second. So it's basically decoding the unpacking stub, and then it gets to this virtual Alec. And then we're going to do Control F9, F8, and then hex dump, Control G, and EAX. So I can put my breakpoint on the allocated memory. So I will right click, breakpoint, hardware access, and byte. And then F9, we see our first byte writing out. F9 again, and we can see the copied out encrypted file. Again, in this case, because it's simpler, we didn't have the API list at the top of it, so we didn't have to do the second copy. So F9 a couple times until we see the MZ header decoded. We see the MZ header decoded. We scroll down, and we see the text section starts at 400 hex. So we have a bunch of null padding for the end of the header, followed by a bunch of new bytes. So we can go ahead and dump this out. And this is our file state, so 21 Bravo. I'll go to memory map. And I'll go down to the 21 Bravo, right click, dump memory to file, and put this in my demo folder. Pull this up in PE bearer. And we'll do the same thing before. We just need to clean up the last section. So we're going to go from the relocations, the last section, from 40800 plus 1600. So go to 40800 plus 1600, and we need to go to 41 echo 00. So we pull this up in HXD, Control G, 41 echo 00. And we see here now there is bytes after this because this unpack file didn't stop at the end of the heap memory. It stopped short. So we're going to hit Control Shift N, and then literally just delete everything after the end of the file. And then go ahead and save that. We'll close this down. And now if we open this up in PE bearer, this will be the file state non-modified. And then we can grab this hash out and search for it. Or again, if we dump this out of multiple samples, we could compare these hashes to make sure they're identical. Because if you dumped it out of memory or use an automated solution that dumped it out of memory in the memory state, you'd have to open it up as like a disassembler and start analyzing it to see if it's the variant, if it's the identical copy, if there's any changes. So by doing it this way, you'll get the same hash every time. So there's no need to analyze an exact copy of itself. But if you would dump this out of memory, there's no way you would know that. And you'd be forced to analyze every dumped out sample to try to see if they have different indicators because you don't have the hash to go off of. All right, so that's all there is for that second sample. So I hope you can see how easy that is. Yeah, it's a quick trick that will work, good portion of the time, probably 80% plus of pack samples, particularly for custom pack that just do the manual mapping, which is the most common form of packing outside like UPX now, at least for the samples I see. So again, this trick won't work all the time, but it'll work a good portion. And so if you want to know a little bit more details of how this works, the rest of this video, I'm going to walk through how to identify that the sample was packed, look over the unpacking stub a little bit, so that way if this trick doesn't work and you need to do slight modifications or understand a little bit better, you'll kind of know how we came up with that trick and kind of what's going on underneath the hood. So first, let's try to identify, we're just going to do this with one sample, but let's try to identify how to know that the sample is packed. So we can open this up and detect it easy. And I just go look at the entropy. You can see here this one section, the last section of here, has this entropy above 7, and so detect it easy thinks it's packed, and it turns out it is packed. So that's not a guarantee, but that's a good indication that you probably are packed. So now that you suspect it's packed, Usually what I do is actually just open up straight in Ghidra. And so I'm going to open up this sample in Ghidra and go to my graph view. Now, if you watch the video I've had previously on how to find the start of actor code, you'll notice this address to entry point code is not the standard graph for kind of WinMain. So that's your first indication if you're looking at this assembler that it's not packed. Because packed code very rarely will have an address to entry point that the compiler adds. Normally you overwrite it with the unpacking stub. And so just the fact that this address entry point code is different lets me know that it's probably packed. As I scroll through here, I see the repeated call to the same function with no big arguments. So let's double click this. And I scroll through here and not really see any major API calls. But I see, not really anything there. So I'm going to hit Alt left to get back. And I'm really just looking through here since I think it's potentially packed. I'm looking to see, are the API calls standard? Did it look malicious? Or did it look like kind of unpacking stub? Or a filler code? So as I mentioned, this sample of Qbot actually unpacks overwriting this original section with the unpack code. And one of the ways you can tell that is as I'm scrolling through, I see this load cursor from file. I keep on scrolling. I see you're filling all these stack variables just with the one, and then delete ENH meta file. So I've never seen this delete ENH meta file API before. That doesn't mean it's not a legit API, but oftentimes if you see all this code that looks non-standard and the APIs you've never seen, it's because you basically have filler code. And if I suspect it's packed and then I see what it thinks is filler code, my suspicion is that I'm going to be overwriting this code with the unpack stub. Because basically most of this entry point code, a little bit of it is going to unpack the unpacking stub. It'll jump into that, and then unpacking stub will unpack the file and map it over this original code. So the majority of this code is just garbage code used to fill up space so that you have a section big enough to hold the unpacked file. So again, I can keep scrolling through. I see the same function called over and over again with no real different arguments. Keep on scrolling. I see a sleep here. I see instead of my stack variables, there's a delete ENH meta file again. So nothing that really makes me think that it's a malicious code. So my really anticipation is that it is just going to overwrite the address of entry point with the unpacked file. If that is the case, let me show you one more trick. So that's really all I'm looking for when I look statically. That would be enough for me to say, okay, I think this is packed, and I think it's going to overwrite the entry point code with the unpack code. Let me go ahead and close that down. And now that I have this suspicion, let me show you one more unpacking trick. So I'm going to pull this sample up in x32 and hit F9 to get into the user space. Now this trick only works if you're overwriting the original code, like address entry point, with the unpacked code. So it's not a generic trick, the last one, it's a little bit more specialized, but it's good to know just to add to your toolbox. So because we're overwriting the address entry point code, I can get Control G to go to 400,000 hex, and we see the MZ header. Actually, let me go to the bottom here. So Control G, 400,000 hex, and I'm going to put a breakpoint here. I'm going to do a right click. I'm going to do a breakpoint. Instead of the access, I'm going to do the hardware write and then just the byte. So because basically I can now use my knowledge that it's packed and it's probably overwriting this address entry point, that when it starts to overwrite this with the MZ header, that's where I'll be reading from the file state to map it into the memory state. So now I'm just going to hit F9. Now I'm going to hit F9 again. And basically wait until I hit my breakpoint. Alright, sorry, I still had the call on virtual Alec. So let me take that breakpoint. Let me take all my breakpoints off and start over so we get a clean state. We're going to reset this. F9 to get a memory space. And then we'll go add our breakpoint again. So Control G, 400,000 hex. And then we'll right click, breakpoint, and hardware write this time, just a write. And then we're going to F9. And we're basically waiting until it unpacks the unpacking stub. And the unpacking stub is going to go through and overwrite this address entry point code. So we'll give it a second. So we see here we overwrite it with a null. That because the first byte is basically zeroing out the original code. We F9 again, and now we see it zeroed it out, and we wrote the 4D. And we basically just look at the code where we came from. And this is just like we saw before. This is the copy code coming from EDX into ECX. and through the AL register. We see ECX is our 400,000 hex. That means EDX is where we're coming from. So in dump 2, I'll hit Control G and go to EDX. And we see our MZ header here. If we scroll down at the 400, we see the start of text section. So we could dump it straight out there. So that's one more trick for you to know about. Again, it's a little bit more of a niche trick, but the more tricks you know, the easier it is to do this. All right, so let's close that down now that we have that trick out of the way. And let's look at the unpacking stub to kind of finish out this video. So I'm going to open up the graph view. So this unpacking stub is going to load, zero out some memory, load imports. It's going to get some, what I call position independent code offsets. You can see if we just go in here, you're really just getting, let's go into the sub function again. And you're just getting a positioning off of this file. So it's nothing really important for the unpacking stub. So once we get that, so we get a couple of those, then we're going to allocate some memory. From that memory, we're going to copy the file into the memory. So this is where we copied. If you remember, we, after like what looked like a compressed file, we copied into this new heap memory, and then we go through and decode it. In this case, if we look at it, even though it looked compressed in the debugger, we can see this is basically a single loop, and all we have is this XOR and this add. So it's actually a pretty simple encryption. It just makes it look like it was compressed based on the kind of the format, but all it is encrypted, so that's why it could decrypt it in place without having to allocate more memory. So I'll left arrow key to get back. So now that's decoded, we go in the load library manual. This is just where you map the file state into the memory state. So this is all load library does. So generally, I call that unpacking process load library manual. So I'll double click it. All right, so we're just going to walk through the steps. So the beginning, we have a call to these ECXs a bunch of times. This is just background code that's not actually part of the mapping state, so I'm going to skip over those. And now we get into basically what's the unpacking stub or the load library process. So we would do this memset and we zero out the address to entry point code. And then we copy over the header section. And then we get inside this loop and we copy over the section by section for the loop. We know we're going section by sections because we look for register plus 6, and that tells us the number of sections. I'm going to point out these constants, but I'm not going to go into detail because it literally takes, I have a full day training class where we go over all these constants. So right now I'll just point them out so you've seen them, but don't worry too much about what they are. But so we see a loop with the register plus 6 that tells us it's going through the sections. After we copy our sections, we copy the header over and each section. Now we build the import address table. I know it's built in the IAT because I see a register plus hex 80 that tells me I'm parsing the import data directory. And then if I really want more details, I can scroll through. I see an outer loop with a call here that's going to be called with something like load library. And then I see an inner loop, and I'm going to see another call here. And this is going to be get proc address, either by ordinal at this top one, or by the API name, the string name for the bottom one. So Alt left to get back. Once I build my import address table, I'm going to fix up the relocations. I recognize that because a register plus alpha 0 tells me I'm looking at the relocation table directory. After that, I can see this register plus 6 inside of a loop. That means I'm parsing through the sections again. The only step I have left to parse through sections is this virtual protection stuff. So this is getting your contents ready and then calling actual virtual protect. And that's all there is to this unpacking stuff, the load library manual. I'll hit Alt left. And once we map that into memory, I had this push return is going to do the jump into the address to entry point location. And that's all that you're doing to unpack the stub. So I hope you can see how easy it is for these to use these tricks to dump this out of memory. So that means you're not relying on tools or automated solutions like UnpackMe or tools on the box. You know what you're doing. You can modify these tricks based on your understanding of the unpacking process if you get variants or things of the nature. And more importantly is you can make sure you're getting a file state out, and that way you know when you get a hash, you know it's the hash that's not changing. And then if you dump this out of variants or different pack files with the same payload, you know you're getting either the identical payload out or you get a different payloads. You need to analyze them in more depth. So I hope you enjoyed the video today. If you did, please like the video and subscribe to my channel to get notified when new videos come out. I also love to know what you think, so leave me comments below. If you want more reverse engineering tips, follow me on Twitter. If you're interested in structured training, check out my website for the malware analysis classes I offer. Until next time, keep on practicing and try to learn something new every day.